Let's look at a second example. This is example 9.4 from the OpenStax textbook, where we'll again use calorimetry data. This time we'll use the data from a calorimetry experiment to determine the specific heat of a metal sample. And then we're going to determine a likely identity for the metal based on the value of its specific heat. So a couple of reminders before we get into it. First and foremost, all our calorimetry problems are ultimately solved using the calorimetry equation Q equals mc delta T. The challenge in all these problems is defining system and surroundings and making sure you match the right constants to how the heat is flowing from the system into the surroundings. And so it's important to be able to decipher and parse the information in the word problem so that you can get an accurate picture in your head of what constitutes the system and what constitutes the surroundings. And the only other thing to keep in mind is to watch your units carefully. Don't do these calculations without including units in the calculations. Taking a little bit of time to write the units down will really help you make sure you're calculating your values accurately, because if your units don't work out to what you're looking for, you've probably made a mistake in your setup. All right, so in example 9.4 from the textbook, we're told that we have, again, a piece of metal cooling down in a calorimeter. We're going to use the data from the calorimetry experiment to determine the specific heat of the metal, and then based on the specific value of the specific heat, we're going to come up with a likely identity for the metal. A 59.7 gram piece of metal that has been submerged in boiling water was quickly transferred into 60 milliliters of water. The initial temperature of the water is 22.0 degrees Celsius. The final temperature of the water is 28.5 degrees Celsius. Use these data to determine the specific heat of the metal. Use this result to then identify the metal based on the value of the specific heat. So our overall problem-solving strategy here is we need to figure out the amount of heat lost by the metal, and we're going to use that to figure out the specific heat of the metal. Notice in our given piece of information, we have the mass of the metal. We don't know its specific heat. That's what we're looking for. And we don't know the initial temperature of the metal. So our big strategy here is we're going to use the fact, once again, that the heat lost by the metal must be gained by the water that's in the calorimeter. Negative Q system equals Q surroundings. So we want to start laying out the constants that we know, and we're going to use negative Q sys equals Q surroundings to figure out the specific heat of our metal. We know that the mass of the metal is 59.7 grams. We know that there were 60 mils of water in the calorimeter, so we can figure out the mass of the water, once again using the density of the water. 60 mils of water, density of water is 1 gram per milliliter, so 60 mils of water has a mass of 60 grams. Mass of a metal is going to be our mass of the system. Mass of the water is going to be our mass of the surroundings. The initial temperature of the water was 22.0 degrees Celsius. The final temperature of the water, once the metal had released all its heat into the water, was 28.5 degrees Celsius. If we need to, we can also once again assume that the final temperature of the water is the same as the final temperature of the unknown metal, because they'd be in thermal equilibrium with one another. So again, the general principle here is going to be that the heat lost by the metal is equal to the heat gained by the water in the calorimeter. Negative Q sys equals Q surroundings. So we want to find the heat absorbed by the water, Q surroundings, and then we can use that to figure out how much heat was lost by the metal. We can calculate the heat gained by the water using our usual calorimetry equation. Q surroundings equals mass of surroundings times specific heat times the change in temperature. We can find delta T, the change in temperature, by taking 28.5 degrees Celsius minus 22.0 degrees Celsius. Delta T, remember, in terms of the sign, is always final temperature minus initial temperature. So delta T is going to be 28.5 degrees Celsius minus 22 degrees Celsius. The specific heat of water we've gotten from table 9.1, and we can get it again. To 4 sig figs this time, it's 4.184 joules per gram degrees Celsius. Mass of the water is 60.0 grams, so there's actually 3 sig figs in the mass measurement. Notice I've included units on everything here. So our heat gained by the water is going to be 60 times 4.184 times the difference of 28.5 minus 22.0 degrees Celsius. In terms of units, grams cancel with the grams in the denominator of the specific heat. Degrees Celsius cancels with degrees Celsius in the denominator of the specific heat, leaving us with an answer in joules, which is how we usually like our heat energy transferred to look. So we have 60. So if we first take the difference, 28.5 minus 22.0, we take this result and multiply by 4.184 times 60. We find that the heat gained by the water is 1,631.76 joules. That must be the same magnitude of heat lost by the metal, just the sign is different. So the heat lost by the metal then is negative 1631 joules. And now we can use that and use the same calorimetry equation, but this time we write it for the system, where the system is the piece of metal that's losing the heat. Qsys is equal to the mass of the metal times the specific heat times the temperature change. All right, so here's where we have to do something a little bit clever. We need to solve this expression for the specific heat C. But we don't necessarily know explicitly we don't explicitly know the initial temperature of the unknown metal based on the data given in the problem. They don't just come right out and tell us. If we read the problem carefully, though, we see that the piece of metal was submerged in boiling water. So we have to make one assumption here to get us our final temperature. In quizzes or exams, I won't do this to you, but in sampling problems or in book problems, you may sometimes have to do something clever like this. If we assume that the boiling water is at a low elevation, the water must be boiling at 100 degrees Celsius. And so if the water is at 100 degrees Celsius, the metal must be in thermal equilibrium with the water, and so the temperature of the metal can only be 100 degrees Celsius. So we can find our delta T for the metal by assuming that by immersing the metal in the boiling water, the final temperature of the metal must be 100 degrees Celsius. So here we have delta T is 28.5 degrees Celsius minus 100 degrees Celsius, and that gives us our delta T. Now we can put in the mass of the metal and solve this equation for the specific heat, where we have the negative of the heat gained by the water, 1631.76 joules, is equal to 59.7 times the specific heat times the difference between the final and initial temperature for the metal. The final temperature, when it cooled down after being in contact with the cold water in the calorimeter, 28.5 degrees Celsius. The initial temperature, 100 degrees Celsius. So first we evaluate this difference, and then to solve for C, we're going to divide by the 1631.76 by the 59.7, and the difference of these two temperatures. So the difference of those two temperatures is negative 71.5 degrees Celsius. The specific heat of the metal is equal to negative 1631.76 joules divided by 59.7 grams divided by negative 71.5 degrees Celsius, giving us a specific heat of 0.382 joules per gram degrees Celsius. Now, to solve the problem, we would identify a likely candidate for the metal by taking this number back to table 9.1. And in table 9.1, we see a metal with a similar specific heat to what we just calculated is copper, with a specific heat of 0.385 joules per gram degree Celsius. Of the candidates in table 9.1, that's really the only metal with a similar specific heat. So we think that our metal is likely copper based on the specific heat value that we calculated. And particularly if the metal that we could see in the real world when we were looking at it was also shiny and copper colored, we would definitely assume that the metal is copper. So here we've used calorimetry data to come up with a specific heat for a metal based on a calorimetry experiment. Once again, when working these as word problems, the challenges are drawing lines correctly between system and surroundings and interpreting the information given in the problem so that it's clear which values we need to plug in each part of the equation. The mathematical operations are pretty straightforward.